Hi, distinguished judges and fellow math enthusiasts. Today, we are going to embark on a journey that challenges the very boundaries of human logic. We are exploring infinity. In our daily school lives, we often treat infinity as if it were a single, ultimate destination, the biggest thing imaginable. We think that once something is infinite, it cannot possibly get any larger. But in poor mathematics, this assumption is fundamentally wrong. Infinity is not a single number, it is a landscape of different sizes. To understand this, mathematicians divide infinity into two primary realms: countable infinity, represented by the Hebrew letter Aleph Nun, and uncountable infinity, represented by the continuum. A set is countably infinite if you can put its elements into a specific order and assign a label to each one, item number 1, item number 2, and so on. Just like the natural numbers. Uncountable infinity, however, is so incredibly dense that no mathematical order can ever contain it. To test the absolute limit of these two realms, we use a legendary thought experiment created by mathematician David Hilbert, the Hilbert's Grand Hotel. Imagine a hotel with a unique property. It has a countably infinite number of rooms, and right now, every single room is fully occupied. The sign outside clearly states no vacancy. In our finite world, if a hotel is full, you are out of luck. But at Hilbert's Hotel, the rules of reality are rewritten. A new guest arrives, desperate for a room. The manager smiles and applies a simple algebraic shift. He makes an announcement over the loudspeaker. Attention! All guests, please move to the room number equal to your current room plus 1. This means the guest in room 1 moves to room 2. The guest in room 2 moves to room 3. Generally, the guest in room n moves to room n plus 1. Because the rooms are infinite, everyone shifts simultaneously and nobody is left without a room. What happens to room 1? It is now completely empty. The new guest checks in legally. Mathematically, we just proved that infinite plus 1 is still equal to infinite. The hotel was completely full, yet it easily made room for more. The challenge escalated. A moment later, an infinite long bus pulls up to the entrance. Inside this bus is a countably infinite crowd of new passengers, all demanding a room. If the manager tries to move guests one by one, it will take an infinite amount of time, so he switches to a beautifully elegant algorithm using the mathematical properties of even and odd numbers. He requests all current guests to multiply their room number by 2 and move there. The guest in room 1 goes to room 2, the guest in room 2 goes to room 4, and the guest in room n goes to room 2n. Suddenly, the current guest occupied only the even numbered rooms. This brilliant move instantly frees up every single odd numbered room 1, 3, 5, 7, and so on. Since the set of odd numbers is also countably infinite, the manager simply assigns the infinite bus passengers to these odd rooms. Once again, everyone fits perfectly. In the realm of set theory, two countable infinite added together still result in the exact same size of countable infinite. At this point, Hilbert's hotel seems absolutely invisible. It can manipulate any wave of incoming guests as long as they arrive in the countable line. But now, the ultimate mathematical storm arrives. The massive crowd of unprecedented scale walks up to the hotel. They do not have numbers, and they refuse to stand in the numbered line. Instead, every single person possesses a unique name made of an infinite sequence of the letters A and B. The only rule governing this crowd is that no two people share the exact same sequence of letters. For instance, person 1 might be named A B B A extending forever. Person 2 might be named B B A B B A and on the manager replying on his past victories, confident declares, "Do not worry, I have used our most advanced mathematical mapping and I have successfully packed every single one of these A-B combination guests into our rooms 1, 2, 3, 4, all the way to infinity." Let's test his claim. We look at his manager registry book, which lists the name of the guest he claims to have accommodated. In room 1, we have a guest whose name starts with A B B A extending to infinity. In room 2, the guest name has A in the second position, B A B extending to infinity. In room 3, the guest has B in the third position. In room 4, the guest had A in the fourth position. Everything looks perfect. The manager thinks he won, but he's about to face the terrifying power of Cantor's diagonal argument. Let us play a game of absolute logic. We are going to construct the name of a completely new person using the manager's own registry list. First, we read down the diagonal of the book. We take the first letter of the room's 1 guest, the second letter of the room's 2 guest, the third letter of the room 3's guest, and the nth letter of the room's n guest. We link them together to create a baseline name. In our case, that name starts with AABAE extending forever. Now, we perform the fatal mathematical strike. We invert every single letter in its diagonal name. Wherever there is an A, we change it to a B. Wherever there is a B, we change it to an A. Our brand new inverted name becomes BBAB extending to infinity. Let us ask the critical questions. Which room is this new person's name? Can it be in room 1? No, because their first letter is B, but room's 1 guest start with A. Can they be in room 2? No, because their second letter is B, but room 2's guest has A. Can they be in room N? Absolutely not, because by construction, their name is guaranteed to be different from the guest in room at the exact nth character. This proves an undeniable fact. This newly created person does not exist anywhere inside the Infinite Hotel, even though the manager claimed he filled all rooms. And worse, we can repeat this diagonal inversion to generate an infinite number of these ghost guests who are left outside in the cold. The Infinite Hotel has completely failed. Its countably infinite structure has utterly collapsed under the weight of this uncountably infinite crowd. This elegant exercise is a visual proof of George Cantor's breakthrough theory. The infinite crowd of A-B combinations represent uncountable infinity. It has the exact same cardinality as the continuum of real numbers. Hubert's Grand Hotel is a flawless model for a countable system, but it encounters an absolute barrier when facing the uncountable. It proves to us that infinity is not the end of the line. There are infinities that will dwarf other infinities, making a hotel with infinite rooms look shockingly small. Mathematics is beautiful because it gives us a precise language to peer into these endless layers of existence. Infinity is not the ultimate frontier, it is merely the beginning. Thank you very much for listening to my presentation.